So what we have found during the previous lecture is that we have found an expression for the conserved current, which follows from the Noether theorem. And this current has the following structure. So I denote as Gn mu, and it's given by minus derivative of the Lagrangian with respect to derivative of the field, and then multiplied with response of the variation of the field minus d nu phi I, derivative of the field, response of the variation of independent coordinates, minus Lagrangian multiplied by the same thing, x and nu, and plus probably the contribution from the boundary term. Now, in this expression, I have to stress that these two indices, mu and n, they have a different meaning. So while mu runs the space-time indices 0, 1, and so on in general up to d minus 1, the index n runs the same range as a number of independent parameters which give rise to variations. So n runs from 1 up to s, in a sense that we have s independent continuous variation parameters. Continuous variation parameters. And with respect to index mu, we have a conservation law. Divergence of J mu is equal to 0 on shell, which means on solutions of equations of motion. On solutions of equations of motion, the same as Euler-Lagrange equations. Now, the local conservation laws, this means these laws here, can be used to define, this is valid for any n, by the way, for any n from 1 up to s. These conservation laws can be used to define the integral invariance. We have to assume that all fields vanish at spatial infinity, and then define the following integral, which I denote now Gn as Gn, integral of space, of the whole space, of the zero component of the current. So zero component means time component. Time component. So I take a time component of the current and integrate over the whole space. Means that this space is d minus 1 dimensional hypersurface orthogonal to the time direction. So the picture which you might have in mind is the following. You have a time direction here, x0, and then you have a plane which stands here to depict the d minus 1 dimensional space, and this is a space over which you have to integrate the zero component of the current. And then when you construct such a quantity Jn, the statement is that this quantity is a conserved charge, or sometimes people call it Noether charge. Why it is conserved? The reason is the following. So if you differentiate this object over time, So take derivative djn over dx0. Since you integrate over spatial directions, you can move the differentiation over x0 inside the integral. And now it turns into partial derivative because you differentiate now the current, which depends on time, but also on the spatial components. So it becomes partial derivative. But then from the conservation law, from this law here, it follows that if I write it in terms of indices in an explicit way, then this is g0 over dx0 plus dgi over dxi, where here over I, there is a summation and I runs over special indices 1 and so on up to d minus 1. And this must be equal to 0. So this derivative here can be replaced by the divergence now computed with respect to special indices. So you have here, therefore, minus integral over b. I'm thinking about this as about a ball or this surface which I have just drawn. And then you replace this by dgi over dxi. And as you see now, with respect to this space, what is written down here is a total derivative. So you can integrate it, and the integral will be reduced to the integral over the boundary of the space region. Maybe I denote this boundary in this way, like this. Just draw it and denote it as dB. So dB, integral over the boundary of ds flux of Gn through the boundary, of this region here, through the boundary of this region. And so n here is a normal vector to the boundary of this region. So normal vector like this. And so what is written down here is a flux of the vector Gn through the boundary. Now, this boundary actually tends to infinity. So you take it, the boundary, say, for instance, a sphere surrounding this d minus 1 dimensional ball. So it's a d minus 2 dimensional sphere surrounding this ball. And if our fields are assumed to have a vanishing behavior at infinity, then in the limit where this boundary tends to infinity, this integral here tends to 0, because fields are assumed to die, let me say, to die at special infinity and special infinity. If this is the case, if you assume this boundary conditions that actually when you go far away in the spatial directions, your fields your fields vanish, then you see that you have a conservation law in the normal sense of the word. So the integral of Gn over time, or the same of over x0, is equal to 0. And so you indeed derive the conservation law. Now, what we can do, we can apply the general theorem of Noether to the discussion of concrete examples of symmetry transformations, and derive for this examples the corresponding conserved currents. And the first thing I will start with is very simple. It's an example of internal symmetry. So the case of internal symmetry. This is a case where you don't touch the space-time variable x mu. You don't do anything with x mu. So delta x mu is equal to 0. So variation vanishes. And therefore, the only variation you do is a variation of the field. That's why it's called internal symmetry, because it does not involve change of the space-time. So this variation, as we know, is written down as response phi, say I n delta phi epsilon n here, epsilon n, and then we sum n from 1 to s. And then, so the only non-trivial response is this f, this phi, sorry, and therefore, if you just look at the general expression, at our general expression here, we see that only this term here contributes, because x and nu response on variation of space-time is absent. And therefore, for this case, the current looks rather simple. So G and mu, conserved current, is given by derivative of the Lagrangian with respect to mu phi I, and then multiply by response of the field depending on phi. So this is a simple example of internal symmetry transformations. The second very important example is the example of a conserved quantity, which is called energy momentum tensor. Energy momentum tensor. Sometimes this tensor also people call stress energy tensor, simply stress tensor, stress energy tensor, stress energy tensor. And this corresponds to infinitesimal space-time transformations, which we can first start to consider from the case of a single scalar field. So consider simplest example, a single scalar field. And the transformations which we will perform are transformations, translations of space-time coordinates. So x prime mu is equal to x mu plus delta x mu, and this delta x mu is simply a shift, which I can write in the following form. I introduce delta mu, Kronecker delta symbol, multiplied with epsilon nu. Epsilon nu are constant parameters of my transformations, of my shifts, constant shifts. So why I'm doing this? Because this is in this way you read off from this formula that the response x looks like x mu nu equals to delta mu nu. This response is exactly this delta Kronecker, which you see here. And so now for scalar field, we know that the transformation property is phi prime on x prime is equal to phi on x. And therefore, in this case, this delta phi variation, delta phi, is actually vanishes. And therefore, response phi capital In vanishes as well. So there is no phi capital for a case of a scalar field. And the formula for conserved current now looks as follows. For the stress energy tensor, people use a special notation for this current. So instead of G mu n, you can use T mu nu, where index n now is replaced by nu, because n will be running the same range as index mu, as a space-time index mu, right? Because the transformations which you are using are these epsilons, which carry actually the same index nu of space-time. You see it here, right? You see it here explicitly, this index nu. So with this special notation T mu nu for this conserved current, you obtain the following expression for the stress energy tensor. T mu nu is equal to derivative of the Lagrangian, again, with respect to the derivative of this scalar field, d nu phi minus delta mu nu multiplied by Lagrangian density. Or sometimes they use the word Lagrangian, but I mean here Lagrangian density. You understand? So this is how the stress energy tensor looks like for the case of a single scalar field. And this tensor, which is directly derived by applying the general expression of the Noether theorem, this expression here, is called canonical. And I will explain the reason why people use this form of the stress energy tensor, canonical. So this is canonical stress tensor for a scalar field. Or a scalar field. One can ask the next question, so how this tensor will be looking if you consider instead of a scalar field, for instance, a vector field. So let's look at a vector field denoted phi lambda, where lambda is an index, is a vector index. And consider absolutely the same transformations. So x prime mu is equal to x mu plus epsilon mu, which we write as x mu plus delta mu nu epsilon nu. And the question we have to ask is, what is the transformation for the field now? What is the response of the vector field on coordinate shifts? It turns out that actually this response vanishes again in the same way as it was for the case of a scalar field. And this is you see from the following formula. If you consider the variation of a vector field, then this is by definition should be response of a vector field multiplied by epsilon mu. So phi lambda mu multiplied by epsilon mu, where I'm summing over mu. On the other hand, this delta phi lambda is the transformation which comes from the general infinitesimal version of the transformation of a vector under the coordinate change. And you know this formula, we discussed it in the first lecture. So say phi lambda prime on x prime should be given by d x prime lambda over dx rho phi rho on x. This is how the general formula looks like. And the infinitesimal transformation then will be written in the following way. So infinitesimally x prime lambda is x lambda plus epsilon lambda. And you see that in this case, this derivative infinitesimally change of the derivative dx rho over delta x prime lambda is simply derivative of epsilon lambda over dx rho, but epsilon lambda is constant, and therefore this derivative vanishes. And as a result, this variation here vanishes as well, and therefore for the vector field also response vanishes, as it was the case for the case of as it was the case for a scalar field. Therefore, from here we see that the stress energy tensor for a vector field will have a similar form to what you had for scalar, except now you have to sum over vector components. So you have an index lambda, and here you take a derivative with respect derivative nu of this vector phi lambda, and you sum over this component lambda minus delta mu nu multiplied by the Lagrangian. This is how stress energy tensor will look for a vector field. So now we consider a bit more sophisticated transformations, which are related to angular momentum, to the conservation laws related to the conservation of angular momentum. For that, so this is our third example. Let's say this is our third example. Third example, angular momentum. Angular momentum. And for this, we have to consider infinitesimal rotations. Infinitesimal rotations of Minkowski space. Infinitesimal rotations of Minkowski space, which are transformations of the following type. So x prime mu is equal to x mu plus x nu multiplied by epsilon mu nu, where parameters of these transformations, epsilon mu nu, satisfy the following property: epsilon mu nu is equal minus epsilon nu mu. In other words, these parameters constitute a second rank tensor, which is antisymmetric with respect to permutation of indices mu and nu. Now, if you are in 4 dimensions, then such a tensor has 6 independent components. You understand that's because mu runs indices 0, 1, 2, 3, and therefore antisymmetric tensor will have the number of components equal to 4 multiplied by 3 and divided by 2, which is 6. And these 6 components, these are exactly parameters of 6 Lorentz transformations, which include 3 rotations, usual rotations of space-time coordinates, plus 3 boosts, where you rotate between one of the spatial coordinates and the time. Okay, so 6 parameters making this antisymmetric tensor. And now we have to find a response of our coordinates on such a transformation. And we have to take into account that only parameters epsilon mu nu with, say, mu less than nu are independent. Epsilon mu nu with mu less than nu are independent because parameters with mu bigger than nu, they are found from this condition of antisymmetry. This means that we can proceed in the following way. So again, we consider transformation of coordinates, and we represent them in the following form. So as I said, this is x nu epsilon, say lambda nu, where I'm summing over nu. And this I represent in the following form. So I write it as a x nu delta lambda mu multiplied by epsilon mu nu. So you see I introduce this Kronecker delta, but if I sum over mu, then mu will be replaced by lambda, and I return back to the same formula. Now I'm summing over all mu and nu, but I rewrite now this summation as 2 sums. So first the sum mu less than nu, x nu delta lambda mu epsilon mu nu, plus a sum where index mu is bigger than nu, x nu delta lambda mu epsilon mu nu. And now in the second sum here, I will change the index mu for nu, because mu and nu are dummy indices, the dummy summation indices. I replace mu for nu, then tensor epsilon becomes epsilon nu mu, but epsilon nu mu is minus epsilon mu nu. And therefore, the formula can be written in the following way. Sum mu less than nu, x nu delta lambda mu minus x mu delta lambda nu multiplied by epsilon mu nu, and sum now goes over independent components. Independent components. So now we know this response. From here we read off that the response x lambda mu nu, response of our coordinates on such a variation is given by x nu delta lambda mu minus x mu delta lambda nu. This is a response for mu less than nu. These functions x mu nu lambda are defined for mu less than nu. So let's consider again a case of a scalar field for which we have phi prime on x prime is equal to phi on x. Again, from here, from this transformation law, we deduce that delta phi is equal to 0. And again, a response of variation of fields is actually 0 again. So now I'm taking the general form of the Noether current and substitute there this non-trivial response and get the following formula for this current, where now the current actually has two indices, mu and nu, instead of one index n, which we had before. And this current is usually denoted by the letter m. So the general G and lambda, say, is now getting replaced by m lambda with indices mu and nu. And mu and nu now replace that index n, which was running through a number of independent transformations. But now these independent transformations are the transformations with parameterized by two indices, mu and nu, with mu is less than nu. Okay. And so the answer which we get by substituting such response into the general formula of the Noether current gives the following. So derivative of the Lagrangian with respect to derivative of the field, d mu phi x nu minus d nu phi x mu plus Lagrangian multiplied by the response. So x mu delta lambda nu minus x nu delta mu lambda. Conservation law will read now in this way. So d lambda m lambda mu nu is equal to 0 for any mu less than nu. So in arbitrary dimension, this tensor will have d minus 1 over 2 independent components. This is a conservation law of angular momentum. You can call it conservation law of angular momentum. But in fact, you see that it contains, in addition to the usual angular momentum, which you associate with spatial rotations. In addition, you had also conservation laws which are related to Lorentz boosts. Because as we discussed in, say, 4 dimensions, the components here, mu and nu, provide for you in total 6 independent conserved quantities. 3 of them correspond to the standard angular momentum related to the rotations between spatial directions, and 3 other correspond to Lorentz boosts, and with which such a transformation, one of the 6 possible transformations, you associate, according to the Noether theorem, the corresponding conserved quantity. Now let's note the following, that this formula here for the angular momentum tensor can be rewritten in the following way. I will slightly regroup the terms. So I write m mu nu lambda in the following way. I take x nu out and write it as a d Lagrangian over d lambda phi, d mu phi minus Lagrangian delta lambda mu, minus x mu, derivative of Lagrangian with respect to phi, d nu phi minus d lambda nu, like this. I just regroup the terms, split into 2 groups, and then if you compare what is written down in the brackets here and here, you realize actually that what you see is nothing but the stress energy tensor for the scalar field. And so this expression, therefore, can be written as x nu, component of a stress tensor T lambda mu, minus x mu, component lambda nu, where T lambda mu is a stress tensor for a scalar field. Stress tensor for a scalar field. Yeah, very interesting. So tensor of angular momentum has this interesting structure. And what we can do further, we can see now implementation for this expression here of our conservation law. So we know that this stress energy tensor must be conserved. This is the one thing which we know. And we would like to see what it implies now if I write the expression for this angular momentum tensor by using this stress tensor. So what it implies? We see that if I compute the divergence, so I write here d lambda t lambda mu nu, and substitute this representation here as x nu t lambda mu minus x mu t lambda nu, then differentiating x nu, I will get the metric d lambda nu t lambda mu minus or plus maybe x nu d lambda t lambda mu. This is a differentiation of this product, minus eta lambda mu t lambda nu minus x mu derivative lambda t lambda nu. And you see, due to the conservation of a stress tensor, these 2 terms vanish. And using the rule of raising and low indices with the help of the Minkowski metric, you obtain here t nu mu minus t, and here you get mu nu. This is an interesting observation, which I'm going to use a little bit later on. So for the moment, we have just derived this interesting expression, which actually shows to us that for the case of a scalar field, since we know, so this is not T, this is M here, this expression shows us that since by Noether's theorem we have the divergence of angular momentum tensor vanishing, then the stress energy tensor for a case of a scalar field must be automatically symmetric. T mu nu is equal to T nu mu. That's an interesting observation, which comes from this application of the Noether theorem and the explicit form of the angular momentum tensor for the case of a scalar field. But we can ask what happens if we now consider, for instance, the energy momentum tensor for a vector field. So energy momentum tensor and tensor of angular momentum also for the case of a vector field. So m lambda mu nu for the case of a vector field. What it will give us. Now, for the case of a vector field, there is a non-trivial response of a vector on space-time rotations. And this you can find from the following things. That first of all, we know that this must be equal as phi lambda mu nu epsilon mu nu. These are independent parameters of our Lorentz transformations. 6 parameters in 4 dimensions of independent Lorentz transformations. On the other hand, this should be given by the transformation law of a vector under coordinate transformations, which are in this case are just Lorentz transformations. And now I have to substitute here the change of coordinates according to the formula which we have just derived. So x nu delta lambda mu minus x mu delta lambda nu multiplied by all this is multiplied by then phi rho. So I need to apply the derivative to this expression here and then multiply with the field phi rho. So differentiating, performing the derivatives, then you find that this expression here, this response for the case of a vector field is non-trivial and is given by the following formula. These derivatives, you compute the differentiation of x's with lower indices with respect to x's with upper indices, give again the Minkowski metric. So eta rho nu delta lambda mu minus eta rho mu delta lambda nu multiplied with phi rho, and then summing up, you will get phi nu delta lambda mu minus phi mu delta lambda nu. This is how a response will look like for the case of a vector field. And now if you substitute this response together with the response of coordinates into the general formula for the Noether current, you will find for the tensor of angular momentum of a vector field the following formula. It will be written as minus d Lagrangian over d lambda phi rho. And here there will be a longer expression, phi nu delta rho mu minus phi mu delta nu rho plus x mu d nu phi minus x nu d mu phi, bracket is closed, minus Lagrangian density multiplied by x nu delta lambda mu minus x mu delta lambda nu. Okay, so this is how the angular momentum will look like. And again, if you compare this expression, compare to stress tensor of a vector field, you will see that you can write this expression in the following way. M lambda mu nu is equal to x nu t lambda mu minus x mu t lambda nu, just as was before, but this is not the end of the story because there will be extra contribution, which looks as follows. Phi nu here, phi mu minus Lagrangian in lambda phi mu, like this. So in particular, let me maybe here to write explicitly, just stress that these terms here are coming from this term in the expression for angular momentum tensor. So if we look at this expression, we see that it does not reduce to the previous case of a scalar field, because for a scalar field, we had only this part here, but now we have an addition term. And the first piece, which was a case also of a scalar field, is called orbital momentum. Orbital momentum. While this additional piece, it characterizes, as people say, polarization properties of the field. And it's related to the notion of spin. And so this second part here is called spin part. So orbital part and spin part. And so stress energy angular momentum tensor for the case of a vector field splits by construction into two parts, orbital part and the spin part. And what is interesting, if you now look at our discussion of their conservation law, so we know that T lambda mu nu, divergence of this tensor, is given by T nu mu minus T mu nu. That comes from differentiation the orbital part, but then there will be also contribution from the spin part. And from here, you cannot actually conclude that the spin part and the orbital part are separately conserved. You see that this will be the case, a separate conservation of the orbital part and the spin part only if stress tensor is symmetric. If stress tensor is symmetric, in other words, T mu nu is equal to T nu mu, then the spin part will be separately conserved. In general, you don't know if your stress tensor is symmetric, and in general, you may find a non-symmetric tensor. In this case, you have no possibility to actually define two separate quantities because there is no separate conservation of the orbital part and the spin part. But in total, when we add up orbital part to a spin part, it is always conserved because by Noether theorem, it comes from a unique quantity, namely this tensor of angular momentum, which according to the Noether theorem should have vanishing divergence. So once again, stress energy tensor is not always symmetric. In particular, we will study the case of a Dirac field where we will find that the stress energy is not symmetric. And in this case, there is no separate conservation of spin and orbital paths. This is something interesting to have in mind. And my last example of conservation loss and application of the Noether theorem will concern Lagrangians of so-called Wess-Zumino type. Wess and Zumino, these are two scientists who are responsible for seminal contribution to the discovery of supersymmetry. And in some cases, the Lagrangians have the property that they are invariant, or many Lagrangians which have supersymmetry have the property they are invariant only up to boundary terms. And since the appearance of boundary terms is allowed by Noether theorem, we have an examples where there are conservation laws associated to the existence, to the appearance of these boundary terms. And the simplest Lagrangian density which exhibits this property to be invariant up to boundary terms is this Lagrangian. It's the simplest possible example I can write is Lagrangian of the type C mu nu C, let's write this way, C ij mu phi I d mu phi j, where this is a Lagrangian for a number of scalar fields phi I, where I is running from 1 up to some number m. Mu is a space-time index, and these coefficients C, I, J, mu, they are antisymmetric in I and J. So C mu I, J is equal to minus C mu J, I. So this is needed, otherwise the Lagrangian will be a total derivative. And so this antisymmetry property guarantees that you cannot take this derivative out, because if you take it to the left, first of all, you see that you will obtain the minus sign, but then if you replace I for j because of the skew symmetry of these c's, you will return back to the original Lagrangian, and the total derivative term will vanish. So differentiation by parts will return you back to the original Lagrangian because of this property here. So Lagrangian is not a total derivative because of this property. Then infinitesimal transformation of fields phi I, which leaves this Lagrangian invariant up to the boundary term, is a simple shift. When you take a field phi I and shift it by constant parameter epsilon I. And then you see that the variation of the Lagrangian density in this case is C mu ij epsilon I d mu phi j, right? That's because when you will be varying phi j here, it will be replaced by epsilon j is constant, and therefore its derivative vanishes. And so this is how infinitesimal variation looks like. But this, because of the constancy of C and epsilon, you can rewrite as a derivative applied to C mu ij epsilon I phi j. And so this is, as you see, a total derivative. Total derivative. So we write it as d mu lambda mu, where you see that this lambda mu term is C mu ij phi j. And if you write it as lambda mu n, lambda mu I epsilon I, C C mu ij phi j epsilon I, then you see that lambda mu I is C mu ij phi j. So you can now use again the formula for the Noether current. Now index n is our index I running from 1 to m. And we get from Noether theorem, from expression for the Noether current, the following expression. D mu phi I, this is the first term, and then contribution from lambda. And contribution from lambda is C mu I j phi j. And if you now take our Lagrangian here and differentiate it with respect to derivative and plug it in, you will get minus C ji mu phi j plus Cij mu phi I. You will find that this is simply twice Cij mu phi j. This is index j here. Okay, so this is how Noether current looks like, and you can immediately test the conservation law. So you take this current and compute its divergence. It reduces to, as you see from this formula, twice d mu applied C mu ij phi j. But this is equation here is nothing as a equation of motion for a field phi I. This is, you see from this Lagrangian here, taking the variation with respect to phi I, you get exactly this expression here. And so on solutions of the equations of motion, as should be according to the Noether theorem, the divergence of the corresponding current vanishes. So these examples exhaust my considerations of possible symmetries of the conservation laws. And the further remark which I would like to make, further construction, is the so-called improvement procedure. Improvement procedure. Improvement procedure, which sometimes is important to have in mind. The point of this discussion, which I'm going now to present, is that in principle, the conserved current G n mu is not uniquely defined. Is not uniquely defined. Of course, as we have seen, the Noether theorem gives us a very concrete expression for this current. And in a way, this current is called canonical. But it turns out that you can change this current by adding to it the so-called improvement term. So you take your canonical current, canonical, which means derived by the canonical procedure from Noether theorem, and add to it the following term, which sometimes people call topological. Add to it the divergence of a tensor chi, where this tensor chi is assumed to be skew symmetric in indices mu and nu. So this chi has a property that it is skew symmetric by construction. Then you see that if you add up such a term, you don't change the conservation law. You don't influence the conservation law, because if you now act with a derivative d mu and compute the divergence of this extra contribution, you will get this expression here. But since derivatives commute d mu and d nu, while the tensor chi is skew symmetric and this index is mu and nu, then the result of this is 0. How you compute it, you change indices mu for nu, you get minus the same expression, And so expression is equal to itself with a minus sign, which means that it is 0. So in other words, adding this term does not break the conservation law. Moreover, if chi is a function of fields which vanish at infinity, it also does not break the conservation of the Noether charge, because what you need to add is integral over the ball of the quantity d nu chi nu 0, chi 0 nu, where this is a time component of this function chi. But then this is here because you write because you see that d0 chi 0 0, if we write explicitly what is this derivative, you write it as a d chi 0 k, where k here runs spatial directions. Since chi is skew-symmetric, its 0 0 component simply vanishes, and therefore you have here minus integral dx over the ball of divergence with respect to this space, and therefore, as before, it gives you a flux of the corresponding vector chi 0 k, and over the boundary of this ball. And since the boundary tends to infinity, then this tends to 0, because fields of which chi is made of, they tend to infinity at the spatial boundary. Okay, so this means that in principle we have this possibility, and you can ask yourself, is it possible, for instance, to use this freedom to make your stress tensor, which might be originally not symmetric, to become symmetric by adding a proper improvement term? In other words, you take a T menu and add to it the improvement term, which for this case will be a divergence d rho chi rho mu nu, where according to the discussion we had, this chi must satisfy this property. Rho mu nu must be equal minus chi mu rho nu. Can we make the new tensor or improved tensor to be symmetric? And if we can do that, then as we just discussed, then separately we will get a conservation of the orbital part and the spin part. So is it possible or not? It turns out, well, the answer to this question is that it turns out that there exists an improved symmetric stress tensor. Let's denote it by, say, this letter J mu, which is symmetric if and only if and only if canonical stress tensor T mu, the antisymmetric part of T mu is the total divergence, is a total derivative. Okay, so this is the answer to these questions. So there exists an improved tensor T mu, which is symmetric for an original tensor T mu, if and only if the antisymmetric part of the canonical or original tensor T mu is a total derivative. Now, first we assume that the total, to prove this statement, first let's assume that the antisymmetric part is a total derivative. So it is the rho of some omega rho mu nu, where obviously this omega satisfy this antisymmetry property with respect to indices nu and mu. because you see the left-hand side is antisymmetric in mu and nu. First, let's assume that indeed we have a canonical tensor whose antisymmetric part is a total derivative. Then let's prove that we can always improve such a tensor by adding to it this improvement term, the proper improvement term. To construct this improvement term, we do the following. We take this improvement term chi rho mu nu in the following form: 1/2 omega rho mu nu plus omega mu nu rho minus omega nu rho mu. Take this omega, which we find as an antisymmetric from the antisymmetric part of tensor T, and then perform this combination of these omegas with these indices permuted. Then we see that, in fact, this tensor chi has a desired symmetry. So chi rho mu nu is equal to minus chi mu rho nu. Well, you see it explicitly from this formula. If I change indices rho and mu, what I will get from this formula, you get chi mu rho nu is equal to 1/2 omega mu rho nu plus omega rho nu mu minus omega nu mu rho, right? And now, because this omega has the property of skew symmetry with respect to the last two indices, you rewrite it as a 1/2 minus omega mu nu rho minus omega rho mu nu plus omega nu rho mu. And let's now see that this term here, mu nu rho, is minus this guy. This rho mu nu is a minus this term, and the last one is minus this term here. So indeed, this function, this tensor chi, does satisfy the symmetry property we want from it. And second, if you take chi as defined by this formula here and subtract chi with indices mu and nu permuted like this, then we get from this expression here the following answer. This is nothing else as omega rho mu nu. Please check me. So take this tensor here, change indices mu for nu, use the symmetry of omega, and you will find that this is just omega rho mu nu. Therefore, in this antisymmetric part, I can substitute instead of my tensor omega rho mu nu this difference chi rho mu nu minus chi rho nu mu, like this, and then you open chi rho mu nu plus d rho chi rho nu mu, and you see now that you can combine t mu nu with putting this derivative to the left, d rho chi rho mu nu, and t mu nu, this guy, you put to the right, plus d rho chi rho nu mu, from where you conclude that this tensor J mu nu, defined by the sum of t mu nu with this divergence of chi, is a new tensor which is symmetric. It is symmetric and is conserved by the fact that we have added the proper improvement term, which does not break the conservation law. So indeed, we have proved that if antisymmetric part of the stress tensor is a divergence, is a total divergence or total derivative, then the stress energy tensor can always be improved by adding a proper improvement term. The other is that the other way is say we have assume we need to assume the opposite, that there exists an improved symmetric tensor, which means the tensor T mu nu is given by T mu nu plus an improvement term. So improvement term does exist, which makes original tensor symmetric with respect to permutation of indices mu and nu. But then from here, it automatically follows that the antisymmetric part of T mu nu is a total divergence, because you take G nu mu, and this is T nu mu plus d rho chi rho nu mu. You subtract from the first expression the second one, and you get T mu nu minus T nu mu equals to d rho chi rho nu mu minus chi rho mu nu, which shows that indeed antisymmetric part is a total divergence. And so the opposite statement is also proved. The tensor chi rho mu nu, which is skew symmetric in indices rho and mu, in which you can, whose derivative you can add to improve the stress tensor. This tensor has a name of Belli-Infante tensor. Sometimes people call it Belli-Infante tensor. Belli-Infante tensor. And the final remark concerning this improvement procedure is that even improvement is not unique. Suppose you have a symmetric tensor. So suppose you start from a canonical tensor and then you improved it by adding a proper Belli-Infante tensor and making your tensor symmetric. But even if your tensor is symmetric, you can still add to it the following further improvement term. You can improve further, or you don't improve, in fact, anything, but just you change the tensor T mu nu by adding to it a following object. So two derivatives, d rho d sigma, applied now to tensor of the fourth rank. So it's tensor which has four indices, mu, rho, nu, sigma, where you require from this tensor W with four indices the same symmetries as the symmetries of the Riemann tensor. Riemann tensor. And the letter tensor is constructed constructed by using the metric, and it's known that the Riemann tensor has the following symmetries. So it is skew symmetric with respect to each pair of indices. So minus W rho mu nu sigma. It is skew symmetric with respect to the second pair of indices. So W mu rho sigma nu, and it is symmetric under simultaneous permutation of pairs of indices. So mu rho nu sigma is W nu sigma mu rho. So if you have such a tensor and you add up it with two derivatives on W, then you will still have a conserved tensor, and it still will be symmetric. And then finally, you can find the symmetric tensor directly from a gravitational theory. There is a procedure which produces you straightforwardly a symmetric stress energy tensor. For this, one has to consider the action for field which you are interested in, coupled to an arbitrary gravitational background. So take your favorite field, for instance, a scalar field or vector field, or later on we consider spinor field, and couple it, couple your field to arbitrary gravitational background. background, which essentially means that you couple your field to the metric. Then the action has standard form. So this is, say, in 4 dimensions would be derivative of the Lagrangian density. And the Lagrangian density, in addition to the field you are considering, also involves the space-time metric G mu. Let me denote the determinant of this metric as by letter G. So determinant of the metric G mu. Then it's known that under diffeomorphisms, x prime mu goes to x mu plus psi mu, where psi mu is a vector field. So psi mu, by definition, is a vector which depends on the coordinates of space-time. The metric is known to transform in the following way. Delta G mu infinitesimally is a covariant derivative of vector psi nu symmetrized. So transformation law for the metric looks like this. And this transformation of the metric then induces a transformation of the action. So if you perform a variation of the action under diffeomorphisms, then the action responds in the following way. You need to take the derivative of the Lagrangian with respect to the metric, and then multiply this by the variation of the metric. But variation of the metric is this object here, right? So this would be the variation of the action. And then one introduces a quantity, which is a stress energy tensor in the presence of the gravitational field. By definition, this is twice divided by square root of minus g, where g is the metric, derivative of the Lagrangian with respect to the metric. Yeah, probably I have to write here derivative, variation, not derivative, but variation. Variation of the Lagrangian with respect to the metric. Then in the gravity theory, it's proved that the following identity takes place. If you take a square root of minus g and multiply it with t mu nu psi nu and differentiate it by d mu, so compute the divergence. So actually this is divergence which you compute. Then this divergence can be written with the help of the covariant derivative nabla mu applied to t mu nu psi nu, like this. And this, you can now open these brackets here and write this minus square root of g d mu t mu nu multiplied by psi nu plus square root of minus g t mu nu nabla mu psi nu, like this. And so this means that in fact you can now come back to this formula here and rewrite the variation delta S by integrating by parts. So you have here nothing else as, yeah, first of all, since metric is symmetric, you rewrite this expression as d for x square root of minus g t mu nu nabla mu psi nu. Now I'm just substituting this definition of stress tensor. So square root of minus g will appear because of the definition of t mu nu. It appears back. And now I'm integrating this expression by parts. So I get first the total derivative term d mu square root of minus g t mu nu psi nu. And second term, I have to take minus, and the covariant derivative will be acting on this expression here. But this I can write in terms of the covariant derivative. So square root of minus g d mu t mu nu multiplied by psi nu. Psi nu. Now, if we assume that fields psi nu vanish at infinity, then the total derivative term does not contribute. It gets out. And then, since you want your action to be invariant with respect to diffeomorphisms, and this is the way you couple your field to the gravity, to the gravitational background, you want that the whole action is invariant with respect to diffeomorphisms, then it means that this variation must vanish for any psi nu, and this means that this is only possible if stress tensor satisfy this equation. Covariant derivative d mu acting on t mu nu vanishes. So this conservation law, it's not really a conservation law, because the derivative here is not the usual derivative, but rather it's a covariant derivative, right? It's a covariant derivative which acts on t mu nu, gives you 0. But now, if you are on the flat background, if you now make your metric in this expression Minkowski, then covariant derivative turns into the usual derivative. And from here, from this expression, you deduce that actually on a flat background, this covariant expression involving covariant derivative, covariant divergence, should go to the usual divergence, which means that on a flat background, t mu nu will be conserved in the standard sense. Its usual divergence vanishes. On the other hand, the way you derive it, you return back to this formula, you see that since metric is symmetric with respect to indices mu and nu, the object which you obtain by means of variation Lagrangian with respect to the symmetric metric will be automatically symmetric. So t mu nu will be equal to t nu mu. And so this is a way to obtain a symmetric tensor by coupling your field to the general gravitational background with an arbitrary metric. And then upon you derive this object, you see that it has a meaning, it will have a meaning of the stress energy tensor with the usual conservation law if you then return back in the final equation, to the flat Minkowski metric. So this would be the way to kind of overcome finding the improvement term. If your tensor is not symmetric, you can go directly and couple your field to the gravity in a diffeomorphism invariant way, and then you can derive from this construction the symmetric stress tensor. Now, probably I will come to the questions which you asked me during the week by mail. The first question was about discrete symmetries, such as parity and the time reversal. And in general, you probably have heard about such a thing as CPT invariance, or CPT symmetry, invariance of the action with respect to the combined transformations, namely charge conjugation, parity, and time reversal. So let me say the following. So there are no conservation laws related to discrete symmetries. So Noether theorem is applied only to continuous symmetries. The symmetries which depend on continuous parameters. Discrete symmetries, the Noether theorem for them is not applied. And you saw that we used this continuity very hard in the derivation of the corresponding conserved Noether currents. it does not mean that action is not invariant. The action can be invariant with respect to such transformations as parity, charge conjugation, and so on. But you cannot write down an expression in terms of fields directly by using something like a Noether theorem. Noether theorem essentially amounts to the fact that you can perform continuous infinitesimal transformations. And from here, you derive the corresponding conserved currents. Now, the second question is that when we consider, for instance, Lorentz transformations and ask about invariance with respect to Lorentz transformations, then we usually concentrate on the stress tensor. But what about boosts? Yes, boosts are conserved as well. And this is, you see from this general expression for the tensor of angular momentum, which we have discussed today. Where was it? It was angular momentum. It was here. This tensor in 4 dimensions will have 6 components. I've stressed it several times, which means that it has actually all the generators of the Lorentz transformations given rise to the corresponding conserved quantities. So this means usual angular momentum corresponding to 3-dimensional rotations, as well as to 3 boosts. So boosts are there. They also play a role to build up the tensor of angular momentum. The point which I would like to stress here is the following. The tensor of angular momentum, as well as the stress energy tensor, these are objects which are tensors. So T mu nu, and M lambda mu nu, these are tensors. And tensor nature of these objects means that these objects transform themselves under Lorentz transformations. They are conserved quantities with respect to the time evolution of your dynamical system. So if you have some Lagrangian, Hamiltonian driving the dynamics, then indeed these quantities are conserved. But their numbers, which you compute as components of these tensors, do depend on a Lorentz frame in which you compute them. So if you perform a rotation of the Lorentz frame, if you boost yourself, for instance, with respect to the original frame, then these numbers represented by components of T mu nu and M lambda mu nu, they will be changed. They will go to other numbers, which also will conserve with the time because of the dynamics of your system. They always be conserved, but they will be changed because these objects are tensors. And so from this point of view, you can ask yourself, but what are the quantities which actually characterize your dynamical system in such a way that they are independent on the choice of the Lorentz frame? And in representation theory, in general, these quantities are known as Casimirs. Casimirs, or Casimir operators. Casimirs. And the Casimirs are objects which, first of all, commute with all generators of a Lie group under consideration. So in our case, the group we are considering is a Poincare group. So let's say that in our case, Casimirs will be the objects which commute with all generators of Poincare group. Poincare group. This means that if I take C to be a Casimir, then it must commute with all generators of translations, and generators of translations is p mu are components constructed as conserved charges related to stress tensor. So zero component of say T0 nu, let's write here mu, so mu here, integrated over special directions. And analogously, such Casimir must commute with all generators of angular momentum. And generators of angular momentum are obtained, these are conserved Noether charges obtained by integrating the zero component of angular momentum tensor, again, with respect to the space. And you can ask now yourself, what are the Casimir elements or Casimir operators for the case of the Poincaré group? For the case of the Poincaré group, there are two Casimirs. One Casimir is simply squared of p mu. So p mu squared, it's nothing else as p0 squared minus vector p squared. And in what people say massive irreducible representations of the Casimir group, of the Poincaré group, the Casimir C1, which is just a square of p, of the vector p, it takes the values m squared, c squared, m squared, c squared, yes. So p0 squared minus p squared is m squared, c squared. And if you put it to the one side, then you will see that what you get is what is called mass shell condition for a relativistic particle, which we will study in detail a little bit later. Mass shell condition for relativistic particle. You can check yourself using, I guess I've written down the commutator relations of Poincaré group last time. I've written down the commutator between the generators of angular momentum. This one, look the previous lecture, and also I've written down the expression for the commutator of m mu with momentum, with p sigma. And now if you take p mu, and just use this commutation relation to compute the square of p with another p sigma, you will find 0, and as well as you will do computation with generators m mu, you will also find 0. So square of p mu gives you a first Casimir, gives you the first Casimir of the Poincaré group. And the eigenvalues of this first Casimir in irreducible massive representations of the Poincaré group are characterized by the quantity which is called mass. And this is something which we call mass of a particle. Mass of a particle is the value of the first Casimir of the Poincaré group. The second Casimir, I mentioned that there is a second Casimir, is constructed by using a certain special vector, W alpha or W mu, which is constructed in the following way. You take fully antisymmetric tensor with 4 indices, epsilon, mu, nu, rho, lambda, and you multiply it with p nu, sum over nu, and then you take a tensor of angular momentum with indices rho lambda and sum over rho and lambda. This vector is called Pauli-Lubansky vector. Pauli-Lubansky vector. And the property of this vector is that, first of all, it is orthogonal with respect to this Lorentz invariant scalar product to the vector p mu. And the second property is that it may be used to build up the second Casimir of the Poincare group. Second Casimir of the Poincare group is given by a square of the Pauli-Lubansky vector. Again, you can check by direct calculations that if you take such C2 and you commute it with P sigma, you will find 0, as well as you will do this with M rho lambda, you also find 0. So this is the second Casimir. And the eigenvalues of this second Casimir in irreducible representations, massive irreducible representations of the Poincare group, they look like they look as follows. So you have C2 equals to mass squared c speed of light, and then there is s multiplied by s plus 1, where s is a half integer number starting from 0, 1/2, 1, 3, 2, and so on. And this quantity here, this half integer number, is called a spin. So in other words, irreducible representations, massive irreducible representations of the Poincare group, massive irreducible representations of Poincare group are characterized by two numbers, mass and the spin. And in fact, this is, of course, in accord with characterization of elementary particles. Every elementary particle has a mass and spin, or it's massless. But massless is a separate case. It's another, so to say, series of representations of the Poincare group. Because you see, if you have massless representation, then p mu turns out to be 0, so it's a light-like vector. And this second Casimir is not anymore, this expression is not anymore valid, because in this case, this expression would simply vanish when mass goes to 0. Here, in that case, there appears a new Casimir, which is called helicity. In the massless case, there appears another Casimir operator is called helicity, and helicity coincides with the projection of a spin of a particle on the direction of motion. So let me write it in this way. A scalar product of p with s divided by the modulus of p. This is projection of spin, on the direction of motion. We will talk about helicity in detail when we come to the discussion of the Dirac's theory. Then we will see how helicity appears, why it plays an important role, and why helicity is applied only to the case as a characterization only for the case of massless particles, but not the massive ones. Okay, so from this discussion, it is clear that what we expect from the quantum theory, so what we are going to do, we are going to construct a Hilbert space of states of a given quantum theory. For instance, for the case of a scalar field, this would be a quantum theory of a scalar field, and we can construct, we will construct the corresponding Hilbert space of excitations of this quantum scalar field. This Hilbert space will be infinite dimensional, But what we expect that in this infinite-dimensional Hilbert space of a quantum scalar field, we will find, or we will realize, an irreducible representation of the Poincaré group, because it is a symmetry group of a quantum scalar field. If you go to the vector field, say for instance to the electromagnetic field, the situation will be similar. We need again to construct a space of states of the corresponding field. And in this case, its field is massless, so we should realize a massless representation of a Poincaré group. And so on. Spinor field, the situation will be analogous. Irreducibility means, I don't know to which extent you now studying the theory of Lie groups or simply groups. Let me ask if you are acquainted with the notion of irreducibility. Do you know what are irreducible representations? What is the notion of irreducibility and the notion of representation? Have you heard about this?
Yes,
For me, yes.
Okay, so irreducibility. Yeah.
For me, yeah, I didn't learn that in a mathematical way. For me, that means the representation matrix cannot be blocked, dialogued.
Okay, so we will thank you. We will discuss this in more detail when it comes to the particular discussion. For the moment, what we want roughly say, what we do, what we want to represent the abstract generators. What means representation? It means that we would like to represent abstract generators of our Poincaré algebra by concrete operators acting in some concrete space of states. Okay, so this is what means representation. There are details. There are more, how to say, rigorous mathematical definition of what is meant by representation. But basically, I would like to realize my algebraic, pure abstract algebraic relations of the Poincaré group, those commutators which I have written down for you in the previous lectures, by means of concrete operators realized in a concrete Hilbert space. I want to think now about these objects M mu and P mu as a concrete operators acting on states in some Hilbert space. And representation is called irreducible if there will be no invariant subspaces. Invariant subspaces means that I take a vector from this subspace, act on it with my generators, and the result of this action remains to belong to the same subspace. So I'm not getting out of this subspace. If there are no subspaces except the trivial one, and there's a whole space, then such representation of a Lie group is called irreducible. No, and on the top, we add up a notion of unitarity. So a representation is called unitary if, say, the Lie algebra generators are realized by Hermitian operators. If, say, we realized our Lorentz generators by Hermitian operators, and the same is with generators P mu. And so unitary representations are important because they tell us that probabilities we will be computing will not depend on the particular Poincaré frame in which we are computing them. Because unitarity preserves probability, as you know from probably courses on quantum mechanics. And so in this way, we are interested in constructing unitary, irreducible representations of Poincaré group. And it's known that since Poincaré group is non-compact, in particular it includes the Lorentz group, which is non-compact, then by the theorem from the group theory, it is known that such representations such unitary representations of non-compact group, they must necessarily be infinite dimensional. That's why the spaces in which we can realize such unitary, irreducible representations of the Poincare group, they must be infinite dimensional. And that is one of the reasons also why we will necessarily deal with fields which encode an infinite number of degrees of freedom, on which in quantum theory, unitary irreducible representations of the Poincare group will be realized. Okay, there is remarks which I want to give, an explanation which I want to give on the questions which I received during the week. Once again, there are no Lorentz generators, there are no Noether generators related to discrete symmetries. So discrete symmetries is outside the Noether theorem. There are no conserved currents related to them. Second, Lorentz boosts are also conserved in addition to the generators of angular momentum. Neither stress energy tensor nor angular momentum generators are invariant with respect to Lorentz transformations. This is not the case. These quantities do depend on the Lorentz frame. What does not depend on the Lorentz frame are Casimir operators, and it is Casimir operators that specify unitary irreducible representations of the Poincare group. For the massive case, these are their eigenvalues are mass and spin. For the case of massless representation, this is helicity, which will specify our unitary reducible representations of the Poincare group. Okay, I think for today that is all. If you have questions, please ask.
Yes, I have a question.
Mm-hmm.
So we introduced two different ways to define the stress tensor. One is from the conserved current by itself. The other one is to consider its coupling with gravitational field. Are they equivalent to each other? Just two ways to get a stress tensor.
Up to improvement terms. In some cases, they lead to the same expression, but in some cases, no. For instance, as we will see, say for the case of a spinor field, the Dirac field, the canonical Noether procedure will give you the tensor which is not symmetric. While if you use coupling to the gravitational background, you can always get a symmetric tensor.
So I want to ask it in a more concrete way. We began with the Lagrangian density, and it is invariant under the coordinate transformation, and from that we got energy momentum tensor. And now
look. You have to be careful here. The coordinate transformations, you mean Lorentz transformations. Yes, and then you get a tensor. So the tensor will be conserved, but it might not be symmetric.
Yes, and again, the same Lagrangian, we substitute all the eta mu nu with some general g mu nu and do the variation.
Then you will get symmetric tensor. Then you will get symmetric tensor.
And there will only be an improvement difference between them.
Yes.
Okay. Yes. Thank you.
Actually, I don't know there's such a theorem, but I mean, the general theorem is telling you the following, that if the antisymmetric part of the stress energy tensor is antisymmetric, if antisymmetric part of the stress energy tensor is a total divergence, then you can improve it to find a symmetric tensor. You can always improve it to find a symmetric tensor. If this is not the case, whatever improvement you do, you will not find the symmetric tensor. But you have to be careful, because the second way of defining the stress tensor by using the gravitational background is also a bit non-trivial. you need to understand how to couple your field, whatever field you have in mind, to the gravitational background in a diffeomorphism invariant way. Yeah. So this is here an important requirement. You have to couple your field in such a way that on the arbitrary gravitational background, your action will be invariant with respect to diffeomorphisms. Diffeomorphisms are general coordinate transformations, and general coordinate transformations, these are not the same as Lorentz transformations. They are different. This is just general transformations, general genuine transformations of coordinates, means that in this case, x prime mu goes to x prime mu plus, say, psi mu, where psi mu are not constants, just like shifts Poincare case, but are functions of space-time.
So maybe sometimes coupling need to be non-minimum coupling.
Well, sometimes you have to understand how to do it. You need to apply, say, all usual derivatives should be replaced by covariant derivatives, and you need to understand now how to account the fact that your fields transform under general coordinate transformations in such a way that together with the metric, the whole action will be invariant with respect to diffeomorphisms. You need to covariantize it properly. By covariantize, I mean to put properly covariant derivatives where it's needed in such a way that the whole thing will be covariant.
Okay, thank you.
We will see that indeed, for the case of, say, spinor field, if you just derive canonical tensor, you will see that it is a stress tensor will be not symmetric, which would mean that you cannot actually separate the spin and orbital path. There is a general angular momentum tensor which is conserved, but you cannot split it into two pieces. One piece would be just responsible for orbital conservation, and another piece responsible for spin conservation. We will see that such things indeed happen. Okay, any other questions? Okay, if there are no questions, let me just announce that in the next lecture, we will start considering the quantum theory, and we will try to quantize the simplest possible field, namely scalar, massive scalar field. So quantization, canonical quantization of massive scalar field will be the subject of our next lecture. Otherwise, thank you very much, and I wish you a pleasant day, and we will see and hear each other next Friday.